Welcome back to Chem 4300. In this video, we're going to finish up Chapter 11 on wave mechanics, and now we're going to look at Hermitian operators. Now, when you do an observation on a quantum mechanical system, any physically observable quantity will have to be associated with a real number. You can't observe a complex number in any physical measurement. So that means that any expectation value that you calculate in quantum mechanics that's associated with this real physical observable has to be a real number. And that's true even if the wave function and the operators that we use in this calculation are both complex. So we require that the expectation value is real, meaning that it has to be equal to its complex conjugate, right? And that's true for any real number. And so that means that this integral here has to be equal to the complex conjugate of the same integral. So the quantities in here could all be complex, but these two have to be equal to each other. Now, we use the rules for complex conjugation here, and we can write down that this equality here, which I'm going to regroup over here, that the integral of psi star and then O operated on the wave function psi here, then equals this complex conjugate. And I can then bring this conjugate in, and that's going to change this guy, make its conjugate, and this conjugate, which gives me psi O conjugate and psi conjugate here. And then I'm going to regroup these guys. The last two terms here, I have the operator operating on psi, and that in parentheses I use its conjugate. And now I have this condition here that I'm going to slide this y over to the other side. And I'm going to have that this integral has to be equal to this integral for this to be true. Now, there's a more rigorous condition that's also true, that the derivation is a little bit more difficult to prove than this one, but this is generally true for any operator that's associated with a physically observable quantity. That operator must be Hermitian, and a Hermitian operator satisfies this constraint here. So let's see if we can look at some examples of operators and determine whether they are Hermitian or not. So let's take this operator, the differential operator. Is this a Hermitian operator? So we're going to check whether this is true, whether this integral on this side is equal to the integral on the right side. And if I put in the actual form for the differential operator, then I'm asking this question over here. So how do we check whether these guys are equal to each other? Well, to do this problem, we're going to have to use integration by parts. So if you remember integration by parts, the integral of u dv is equal to uv minus the integral of v du. So I'm going to look at this over here, and I'm going to assign u to psi star. I'm going to assign v to psi 2. So psi star 1 is u, and v is psi 2, and then du is here, and dv is here. So that will then allow me to use this formula with these definitions to show that this expression here, psi 1 star, and then this is dv right here, so d psi 2 dx is equal to uv, which is now psi 1 star psi 2, and that's evaluated between minus infinity to infinity. Now wave functions by definition have to go to 0 at infinity, so that term is going to go away, and we're just going to be left with this other term over here, which is the v du term. And what we find, I'm going to take it to the next slide here, that term is gone, it goes to 0, and when we simplify down, we end up with this integral over here is equal to the negative of this integral over here. We compare that with what we were supposed to check, and we find that indeed it's actually not true because there's a negative sign here. It has the opposite sign of what it should have. So the derivative operator is not a Hermitian operator because this is not true. Do the same thing with the momentum operator, and you will find that it is Hermitian, that this will be true. But this is an example where we find that it's not true. Now, any operator, whether it's Hermitian or not, you can define something called its Hermitian adjoint using this sort of same approach here. So we're going to define the adjoint of an operator as one that satisfies this relationship with its original operator here. So we saw then in the previous example that the derivative operator here, it has an adjoint which is minus the derivative there. So if you check for the momentum operator, you find that the momentum operator is equal to its adjoint. That's what we need to have a Hermitian operator. So some other helpful theorems about adjoints is that if you have the sum of two operators and you take the adjoint, then it's just the adjoint of the individual operators. The sum of two Hermitian operators is always a Hermitian operator. But if A is not Hermitian, you can find that if you take A plus its adjoint, or I times A plus its adjoint, both of those will be Hermitian operators. So this will be a useful trick that we'll use later in the course. And then if you get two arbitrary operators and you have A times B and you take the adjoint of the product, then it's going to be equal to flipping the order and then taking the adjoint of A and the adjoint of B. Okay, so I think that's it for, oh, one last thing here is that whenever you have Hermitian operators, if you have eigenfunctions of a Hermitian operator, then you can show that this integral over all values is going to be equal to this Kronecker delta function. This isn't the Dirac delta function. This is the Kronecker delta function, which has this result that if m and n are equal, then you get 1. If m and n are not equal, you get 0. So in other words, these guys are orthogonal. So unless m and n are equal to each other, this integral goes to 0. And that's a property of the eigenfunctions of any Hermitian operator. Okay, so this chapter was entirely about sort of the mathematical formalism that we're going to use to solve quantum mechanical problems. So it's a little heavy at times, but generally speaking, we're going to be using these over and over again, and you'll become much more familiar with these concepts as the semester progresses.